Section 2.5 is about the second derivative. So let's go back and take a look at the first derivative for a moment. I'm going to be looking at a simple cubic function, x to the third minus x. And to find the derivative of this function using the limit definition, we compute the limit as h goes to 0, f of x plus h minus f of x over h. This is the derivative function, not the derivative at a point. If this was the derivative at a point, say at 2, we would use 2 plus h and 2. So we take our function f, and everywhere we see an x, we replace x with x plus h. So I have x plus h to the third minus the quantity x plus h. And then I subtract f of x. And f of x is the quantity x to the third minus x. And I'm very careful to put parentheses here. Otherwise, things won't cancel nicely. Now I take x plus h, I raise it to the third power, and I've done that as a little side calculation right here. This is something you can check on your own using Wolfram Alpha or Pascal's triangle. And I'm going to take that result and I'm going to substitute it in right here. So here's x plus h, quantity to the third power, and then I'm going to subtract my x and subtract my h, which I do there. I'm going to subtract my x to the third, and then because of these two negative signs, I'm going to add x. Now let's take a look. We notice that these x's cancel, this x and that x. We also see that this x to the third cancels with this x to the third. And so what we're left with is 3x squared h plus 3xh squared plus h to the third minus h. And just like we usually do, we factor an h out at this point. So we have h times 3x squared plus 3xh plus h squared minus 1. We cancel our h's. And now we can plug 0 in for h. And if we plug 0 in for h, this stays 3x squared, this becomes 0, this becomes 0, and then we have our minus 1. So that means that the derivative function for x to the third minus 1, x to the third minus x is 3x squared minus 1. Now, this makes sense in terms of the graph. Here's the graph in black of x to the third minus x. And in blue, we have the graph of the derivative function, 3x squared minus 1. Notice how the original function has a slope of 0 at about minus a half or so, and the blue graph has an intercept there. That makes sense. The function graph has a slope of 0 over here, so its derivative should be crossing the horizontal axis, which it does. The function is, in this case, increasing up to this point. Therefore, there's a positive slope, and we know that means that the derivative function should be above. It should be positive, which it is. Over here, the slope of the function is always positive, so the derivative function is always positive, and we know that should be true. And right in here, the function is decreasing. The slope of the tangent line everywhere in here would be negative, and we see that the derivative is below the axis there. So that makes sense. Now, the second derivative of the function f is the derivative of the derivative. The second derivative is the derivative of the derivative. So to calculate, we use the double prime notation, f double prime of x. We take our usual derivative formula, but instead of using f, we use f prime. So f prime of x plus h minus f prime of x, all divided by h. And we do the same thing we did before. We take x plus h, but now we substitute it into f prime. So we have 3 times substitute x plus h there, x plus h quantity squared minus 1, and then we subtract f prime of x. And again, we want to be careful about our parentheses. This way things cancel nicely. And I'm going to leave the steps out here, but the process is very similar to what we did before, and the result is 6x. Now let's take a look at this numerically. I have a table of values where x ranges from -3 up to 3, and I'm making the table of the derivative 3x squared minus 1 using those x values. So when x is negative 3, I get 26. When x is negative 2, I get 11, and so on and so forth. Now notice what's happening here. In this range of values from minus 3 to about minus 1, the derivative is positive, but it's becoming less positive. The slope of f is becoming smaller. In other words, f prime of x is decreasing. In here, f prime of x is getting larger. In other words, the slope of f is getting larger, or the derivative is increasing. F prime of x decreasing means its derivative, which is f double prime of x, is negative. Whenever a function is decreasing, its derivative is negative. Likewise, if the function f prime of x is increasing, as is the case in here, that means its derivative, which is f double prime of x, is positive. So let's check that on this graph over here. What I have in black is the original function. What I have in blue is the derivative. And what I have in red is the second derivative function, 6x, which is just a line. Now notice what's happening for the f prime graph. F prime is decreasing, and that makes sense because the slope of f is positive and getting smaller. The slope of f is decreasing. And because the derivative, f prime, is decreasing, its derivative, which is the second derivative, is negative, and we see that right here. Over here, the derivative is getting larger, and we see that on the graph of f. The derivative, or the slope at 0, starts at negative, and then it becomes less negative, but then it becomes positive, more positive, more positive. The slope of f is increasing, which means f prime of x is getting larger, and because f prime of x is getting larger, its derivative, which is the second derivative, should be positive. So let's generalize this a bit. If the derivative is increasing, that means the slope is getting larger. There's different ways that that can happen. Over here, the slope is positive and getting larger. Over here, the slope is negative, but becoming less negative as we move from left to right. So if f prime is increasing, its derivative, which is the second derivative, is positive. And here are two examples of graphs that satisfy that property. On the other hand, if f prime of x is decreasing, that means the slope of f is decreasing. Here the slope is positive and becoming less positive. Here the slope is negative and becoming more negative. F prime decreasing means the slope of f is either positive and becoming less positive, or negative and becoming more negative. And again, f prime of x decreasing means its derivative, which is f double prime of x, is negative. So if f double prime of x is positive, or in other words, if f prime of x is increasing, we might have a graph like this. Likewise, if f prime of x is decreasing, we might have a graph like this. These two graphs have something in common. They both have a cup upward shape. We say that each of these is concave up. These guys have a common property. They have sort of a cupped down shape, so we say that these two are concave down. So let's summarize that a little bit. If the second derivative of the function f double prime of x is positive, that means that f prime of x is increasing. The slope of f is increasing, which means that f of x is concave up. If f double prime of x, the second derivative, is negative, that means the first derivative was decreasing, the slope of f was decreasing, means f of x is concave down. And then we already knew from our discussion of the first derivative function that if f prime of x is positive, f of x is increasing. The slope of f is always positive. If f prime of x is negative, the slope of f is negative, which means that f of x is decreasing. Now, this is a lot to keep track of, and it's very easy to overgeneralize. So here's a general word of warning. If you look at one of the functions, its sign, positive or negative, does not tell you anything about the sign of its derivative. For example, if f of x is positive or negative, it doesn't matter. That doesn't tell you anything about the sign of f prime of x, nor about the sign of f double prime of x. F of x could be positive or negative. That doesn't tell you anything about either of these two. The sign of f prime of x, positive or negative, tells you nothing about the sign of its derivative, which is the second derivative. So be very careful about overgeneralizing. Let's take a look at an example. A nice way to really get an understanding of what's going on here is to take a look at three functions and try to identify which of the three is the function, which is the derivative, and which is the second derivative. A nice way to go about this is to consider cases. Let's suppose that f of x is the black function here. If f of x is the black function, the slope of f is 0 at about x equals 1. Neither the blue nor the red graphs cross at about 1. So again, if f was the black function, the slope would be 0 at 1 or a little bit less than 1, which means one of these would have to cross the axis, and that's not happening. So we can rule that out. If f of x is the blue function, the blue function is decreasing. The slope is always negative, which means the derivative has to be below the axis. That would imply that f prime of x would have to be the black, because the red does not satisfy. But the second derivative would have to be the red by process of elimination. The red is always positive, which means the second derivative is always positive. That would mean that the original function, which is the blue, would always have to be concave up, because if the second derivative is positive, the original function is concave up, and it's pretty clear that the function has kind of a cup-shaped down form there, so concave down, but then concave up over here. So this is not possible either. So that means by the process of elimination that f of x, because it can't be the black, nor can it be the blue, it has to be the red. So let's verify that that's the case. If f of x is the red graph has a slope of 0 at around 2. And that means that its derivative would have to cross the axis there. That means of the two possibilities, the derivative has to be blue. That means since f is red and f prime is blue, the second derivative would have to be black. Let's check that that works. F of x, if it's red, is always concave down, which means the second derivative is negative. And if the second derivative is negative, the second derivative graph has to be below the axis, and that is certainly the case for the black function. So again, to summarize that, f of x is the red, f prime of x is the blue, and f double prime of x is the black. Notice how I handled this by cases, and I used several times these properties. That if the second derivative is positive, that's the same as saying f prime of x is increasing, which is the same as saying f is concave up. And correspondingly, when f double prime of x is negative. What I would like for you to do is to take a look at some examples and try to use a process of elimination to identify which is f prime, and which is the second derivative, f double prime. And I have 3 different examples here. All of these examples are posted in a document under course documents at the Blackboard site. Okay, the document is entitled something along the lines of second derivative graphs. It's a Word document. If you would like to look at more examples, there's a really nice link that I've posted under external links, which will generate various graphs and allow you to guess which is the function, which is the derivative, and which is the second derivative. I want you to be able to identify, but I also want you to be able to explain in the spirit of what I did a few minutes ago.